Hello, this is Dennis Dalton, Safety Officer for Peterson Air Force Base, Rocky Mountain Aero Club. And this is the safety presentation for April 27th, 2021. And this evening is going to be on aircraft performance, a review of the factors that influence aircraft performance on takeoff. Just recently, Enginuity, a NASA mini helicopter, no heavier than a 2-liter bottle of soda, has pulled off the first powered controlled flight on another planet. Flying in a Martian atmosphere is much more challenging than that on Earth. The helicopter's twin counter-rotating rotor blades needed to spin at 2,500 revolutions per minute, 5 times faster than on Earth to accomplish the flight. The air on Mars is less dense. It's less than 1% as dense as the air on Earth, with the density at the surface roughly equivalent to the density at an altitude of about 22 miles above the Earth's surface. The average surface temperature is minus 81 degrees Fahrenheit. So, why there's really no comparison to the Martian atmosphere with Earth? In a way, the ability to extract performance from an aircraft requires a thorough understanding of the power and thrust requirements of your aircraft versus the power and thrust you have available at various conditions of flight. With warmer weather approaching, it's always helpful to review aircraft performance for the T-41 Charlies and Deltas and the 172 Mike. I'm not going to include the RGs at this time or the twin. The concepts are the same. I wanted to keep it relatively simple for the largest amount of people. So we'll start out with air pressure and density altitude. In low pressure air, molecules are diffused and spread out from each other. In high pressure air, molecules are more densely packed, and therefore the propeller produces more thrust, the wing produces more lift, and the engine produces more power. Now, I know for most of you, if not all of you, this is a lot of review, but I think we're going to get into a few things here which seem a little interesting, and I wanted to just go over the basics here. They're using this model here of 1 inch by 1 inch, but any particle or parcel of air, as you've probably seen in numerous books. I'm using a lot of this information from the FAA. I think it's the 8085H pilot's knowledge manual, which is where I get most of my information. As the aircraft climbs higher, there are fewer air molecules. That results in lower pressure air. At higher altitudes above sea level, an aircraft will have worse performance. Heating an air mass causes its molecules to move faster and spread out. Higher temperatures create lower pressure air. So here you have these little simple diagrams, these lines representing the speed of the molecules, I guess, as you want to call it. Blue being the cold and H being the hot. So actually, to me, I sometimes think of these as being actually larger as well than these, as heat expands the molecules. They say spread out is evenly spaced out this way, and that could possibly be true. That they move faster, so they're not as close together. I always thought of it as bigger, but either way, it's hot air is not good. Changes to weather conditions give rise to high and low pressure systems in different ways. Aircraft performance is poor on days with lower pressure. They say air rises in low pressure areas and forms water droplets. Well, the way I think of it, everybody knows that lows are counterclockwise and highs are clockwise. I always try to think of a low as it's like a drain, but it's an upside down drain because it actually pulls everything towards it and then funnels it up because it rises. And so you're actually bringing in things that aren't there. So something's going to change because it's different. A high is taking everything from a top down, where it's smaller at the top, larger at the bottom, going clockwise, and taking everything that's there and pushing it away. So what's there, as long as the high pressure area is right there, it's not going to change the weather pattern until the high dissipates. Air always flows from the high pressure to the low pressure. Humidity. Water vapor is lighter than air, and the higher the temperature, the greater the amount of water vapor that the air can hold. There are no rules of thumb or charts to use to compute the effects of humidity on density, altitude. So take this into consideration by expecting a decrease in overall performance in high humidity conditions. And as you can see, water vapor presented in the atmosphere on humid days reduces the density of air. Water vapor molecules displace nitrogen and oxygen. So we got the oxygen is these little blue things. They got a little graph here, or not graph, but a description up here for you. The red was nitrogen, blue is oxygen. And in zero humidity, they're fairly evenly spaced. The water vapor droplets here, as I previously said, depending on the temperature, they can hold a lot more water, but it's the dark blue things that hook onto the oxygen and make the water vapor, which is then displacing what would be basically usable air as far as the prop, wing, and engine is concerned, which gives it a smaller mass, as you see here, 420 versus 440. I guess that's relative also, depending on the humidity, which I said is difficult to calculate. You just know that it does decrease overall performance. How do we put all this together? Well, at any given altitude, including field elevation, any deviation from standard temperature of 59 degrees Fahrenheit, 15 degrees Celsius, or 2992 barometric pressure must be taken into account. This picture, I think, needs a little explanation. First of all, this pressure altitude can be determined by setting your altimeter to 2992 on the ground or in flight, and note the difference from the reported barometric pressure setting. As long as like me, I'm always going, well, where was it set before? I'll set it to 2992, and then I got to remember where it was and set it back. I don't recall if either of the retractable gear aircraft have a true airspeed ring on the airspeed indicator. That true airspeed ring simply you would find your 2992 and then turn the ring to the pressure altitude and look at the temperature and line that up and give you your true airspeed. But in any event, on the left side, this is considered the ICAO standard atmosphere chart, established as a worldwide standard. This chart represents the standard lapse rate of 3.5 degrees Fahrenheit or 2 degrees centigrade per 1,000 feet up to 36,000 feet. From 36,000 to, I think it's 80,000, the atmosphere is fairly stable. After that, you have the, stratosphere. This chart is used in conjunction with this chart here. Used in conjunction with manufacturers' performance charts to make adjustments for non-standard temperature and pressure. I'll refer to that a couple more times in this presentation. As far as this here, if the air pressure falls, the aircraft will perform as if it is at a higher altitude, or is said to be performing at a higher pressure altitude. If you notice here, these two altimeter settings are both at 30 inches. This airplane's at 5 and this airplane's at 4,000 feet. I think this is a slightly confusing drawing in a way to me. I had to look at this a little bit because basically this illustrates the axiom, high pressure, low pressure, high to low, look out below. In other words, you're going to be lower if you're flying along and never change your altimeter setting to a low pressure area, which, could be who knows what distance. Generally, it's hard to say, but so the thing is if you were setting your altimeter setting and you were at 5,000 feet, this would probably be 2900. They would tell you for this station in this area and reporting station or whatever. And then you would then be up at 5,000 feet, but you would then be higher here because it's a low pressure area to the datum level. So to look at it that way. And I'm sure it's just basically review, but for all the times that you're always getting the altimeter setting, if you don't get it, and you have, to me, it's like, well, you're flying into a low pressure area from a high pressure area, or it's and that's usually a good 4-hour flight where it can make a big difference unless the weather's really bad and you're really flying through a front. So this axiom is true, but this one is a little confusing, as I previously mentioned. When the temperature increases, the aircraft also performs as if it is at a higher altitude. It is said to be at a higher density altitude. Now, you see two temperatures here. Same picture. This one is 86 degrees. This one's 50 degrees. So what he's got here is, these conditions for an RG, 1981 182 turbo. But what he has is 80% of gross weight gives you this ground run. 90% of gross rate gives you a 1675 ground run, and gross rate gives you a 2145 ground run at 86. So if the temperature was lower, the same weights give you a ground run instead of 1290 at 1110. Instead of 90% of gross rate at 1675, if the temperature was 50, it'd be 1430, and at 2145 at gross weight, it would be 1815 at a 50 degree temperature for ground run. Now, this has nothing to do with climb performance. I mean, it does, but it does not. This does not equate exactly to ground. That's just simply the ground run. We'll talk about the effect of ground effect and climb in a little bit here. So in summary, an increase in altitude will cause an increase in density altitude. An increase in temperature will cause an increase in density altitude. A decrease in pressure will cause an increase in density altitude. So it looks like we're going to talk about Leadville just briefly. This computation of density altitude must involve consideration of pressure or pressure altitude and temperature. That is determined by first finding pressure altitude and then correcting this altitude for non-standard temperature. So, question from the 141 Charlie test. Question 17. You're planning to depart Leadville, 9927, field elevation, MSL. The AWOS reports the temperature to be 25 degrees Celsius and the pressure to be at 2880 inches. What is the density altitude? Well, it's not standard because we have 2880. So I'm over here. Here's standard 2992. Altitude adding is 0. 2886. Well, that's not 2880. You got 1,000 feet for 2886. 2880 is a little lower than that. I did the interpolation here, and I've done this question before, it's about 50 feet. So it's 1,050 feet. Okay. Unfortunately, my head is blocking this graph. Great. Because 76 or what is the C? 25C. It's right down here under my box here that I can't get to. So you get the 25 Celsius and you go straight up to 9927 plus 1050, which is going to give you 1077 is just under 11,000 feet. So you're going to go up the temperature chart to 11,000, and then which is going to be right about, geez, it's going to be right about here. I think this is the line right here. And then you go straight over to 14.5. So the answer is B, 14.5, density altitude, which is 997 plus 1050 equals 10. Followed 25C up to 10,977, then left to the 1450. And that's usually the end of the question, but I wanted to take that a little further. This is a picture, of course, of somebody landing on 3-4 to the north, obviously. Do you have enough runway for a ground roll, even without the 50-foot obstacle clearance requirement? Will the airplane climb out of ground effect? Well, we need to talk about ground effect for a minute. That's due to the interference with the flow pattern about the airplane in flight. It can be detected and measured up to an altitude equal to 1 wingspan above the surface. Most people know that, but for the sake of simplicity, I looked at the knowledge book and it said, I'm going to take a wingspan and make it simple, make it 32 feet. It's probably 33 or 34. I don't remember exactly. Well, we're going to say it's 32. Induced drag is reduced 25% by 1/4 of the wingspan from the ground, which is about 8 feet, using 32 feet. So at 8 feet, induced drag is reduced 25%, and just over 3 feet, or 3.2 feet, is 50% of induced drag. And that's quite a bit, So if you take the reverse of that and you say, well, getting off the ground is maybe possible, but climbing past ground effect is not. The 172 surface ceiling is 13,000. T41 is 17,000. Runway 1634 is 6,400 feet. The service ceiling definition for fixed wing reciprocating engines is the ability to maintain 100 feet per minute climb under ideal conditions. So I guess if I was there and we were talking about this, I'm sure a lot of you would have some good advice, some stories. That's mostly what I was trying to present here. Was would it even, it's probably going to get off the ground, but I don't, the one, the T41 would probably get off the ground. The 172 in 6,400 feet, sure, but that would be about it. What we got here, is the left chart, which is these two, this group here, is the 172M mic chart. This gives you ground run performance, right? Ground roll with non-standard centigrade temperatures all along here, because standard's 15, which is right in here, at different pressure altitudes here. This one is the T41 chart, which gives you ground run performance right here with standard Fahrenheit temperatures at 4 specific altitudes, not pressure altitudes. And these are based on the standard lapse rate, basically, which is that chart I showed you, which is 3.5 degrees per thousand Fahrenheit up to 36,000 feet. So, you know, these two different charts illustrate that the importance of reading charts correctly, because these are nowhere near giving you the same information, and you got to do different things to determine what you have to do. Where most of you just fly the C or the D, that's going to be very similar if you go into the RG. You got Cessna's way of doing it. Well, I mean the civilian way of doing it, I think, or maybe a more contemporary way of doing it. Excuse me, which is going to be over in here doing this. I didn't really look at the RG chart. You know, of course, you know, I own a plane, and mine's an early 60s vintage Piper, so I'm ending up with this kind of chart anyway over here. You know, the problem question that we had in Leadville, you know, presented us with a temperature which we couldn't see, it was behind my head, was 76 degrees Fahrenheit. You know, so you know, a temperature of 40 degrees here would probably result in a different barometric pressure as well. You know, as we've all learned from our training, the atmosphere is a gas that will completely fill any void into which it's placed, expanding or contracting to adjust its shape to the limit of its container, meaning lows to highs, hot to cold. So, you know, you take this 40 degrees Fahrenheit, it'd give you a density altitude of about 12,200 feet MSL at that pressure setting that was in the problem. While that temperature would probably work for the 172M to get it off the ground. I don't know about climbing. The M is not authorized for mountain flight in the club. Probably is a word I've pointed out in previous safety briefs as a red flag word when describing outcomes anyway. So every time I use it, I kind of bite my tongue, so to speak. And of course, here I have, I'm sure you're probably over here looking at this. I thought this was very interesting. The Enginuity helicopter, the solar panel was good for 192nd flight per day. What's not on here is I thought I read it was an $80 million airplane. So there you go. The Martian average temperature of minus 81 Fahrenheit means that the range there was negative 220 Fahrenheit to a pleasant 70. That was probably a very interesting but predictable exercise in calculating aircraft performance to get this guy off the ground as well. Of course, it doesn't weigh much. Anyway, I thought the analogy was interesting, so I hope that was somewhat helpful. That concludes the safety briefing for April 27, 2021. This is Dennis Dalton, Safety Officer.